And yeah. Okay, so welcome back. So today Lucas will continue his third talk on the series spin geometry and scalar curvature rigidity. And today he will talk on Llarull's theorem and its generalizations. Yeah, over to you, Lucas.
Yeah, thanks for the introduction. So I wrote down a small recap again from last week. So we talked about spin manifolds, and so it turns out that, or we call a Riemannian manifold a spin manifold if the first and second steeple-Whitney class vanish. So these are topological assumptions here, or conditions. And the justification for this was kind of the construction that we did, namely on a spin manifold for every CLN module W, we can construct a CLTM module bundle, which we called S. And this also carries then a compatible connection. So compatible, I mean a metric connection. So with the metric on S, and it satisfies the Leibniz rule. And this was cooked out of the Levi-Civita connection on M. And this gives us then a Dirac bundle in a canonical way. And we also saw another construction that we can do, namely if we take any emission vector bundle with a metric connection, then we can make twists, namely we can consider the spinor bundle and the tensor product with this E, and then can construct a tensor connection in a natural way. And this again is a Dirac bundle. And in this setting, we saw the Schrödinger-Lichnerowicz formula, which is then a special case of the Weizenberg formula from the first talk. And it turns out that the curvature part of the Weizenberg formula is then once the scalar curvature, which is kind of coming out of the spinor bundle, and also the curvature of the twist bundle, which comes directly from this twist bundle E. And something from the first talk that will be important now is we have a classification for the complex Clifford algebras, namely in even dimensions. The Clifford algebra is isomorphic to the 2 to the k times 2 to the k matrices on C. And in the odd dimensional case, it's twice this. And I mean, what we can do here, we can take the projection entry either to the first or to the second factor here. And then can also see it like this. And from this, we get in a natural way a CLN module acting on C to the K, 2K. And this I want to call sigma 2K. Or maybe not, let's say N, and N is either 2K or 2K plus 1, depending on the parity of the dimension. And actually, it turns out it's a basic algebra fact that so the representation of the matrix group on the vector space, this is an irreducible representation. And also, it carries over to the real Clifford algebra sitting inside the complexified one. So this representation is still irreducible, just because we have these matrices are C-linear. And so we can actually, every CLN module that we can think of, we can describe with as direct sums of copies of this representation here. So yeah, this is kind of the basic representation that we can cook up all the other representations. And we want to consider the Dirac bundle that is induced from this representation. Namely, I want to call it sigma m. This is the spinor bundle associated with this CLN module, sigma n. And then we also have the associated Dirac operator, D, acting on smooth sections on sigma m to smooth sections on sigma m. That is kind of the, if we usually talk of the Dirac operator on a spin manifold, then it's exactly this Dirac operator associated to this irreducible representation. Okay, in the odd dimensional case, we then have two irreducible non-isomorphic representations. And I also want to include this now because this will be quite important. We can twist this. With compatible metric, with compatible connection. Connection. And then we have the twisted Dirac operator on sigma m tensor E. And actually, because of this irreducible effect in the even dimensional case, one can show that actually every Dirac bundle is isomorphic to such a twist bundle here, or a twist. Yeah, let's say every Dirac operator associated to a Dirac bundle can be written as such a twist Dirac operator. So actually, this construction here is exhaustive in the even dimensional case. In the odd dimensional case, of course, this is the second one, but maybe a bit more complicated, but still, this also in this case, this twist construction is exhaustive in this sense. And now I want
I'll just have one quick thing. So like in this regard, if I'll assume the connection to be the usual Levi-Civita connection, then are we getting something special from here, or is it still the same result?
You mean Levi-Civita connection on? I mean, we always start from the Levi-Civita connection on M.
Oh, so these connections are not arbitrary connection; they are Levi-Civita connection.
On M, yes. And then we have the induced connection on S.
Right. But what I'm asking is like, see, your nebula S tensor E, the connection that you have defined there. So that is an arbitrary connection. So that is not need not be a Levi-Civita connection, or that is also a Levi-Civita connection.
So nebula E, you mean this here?
Yeah. On is like.
this is an arbitrary emission vector bundle with a connection that is compatible with the metric on E.
I see. Okay.
Yeah. So now I want to concentrate a bit on the even dimensional case because there's something special in this case. And for this, I want to make a definition. So we take an oriented orthonormal basis of R to the N. And I want to define omega C as I to the K E1 Clifford multiplication up to Clifford multiplication with En. I mean, this sits in CLN. This is called the complex volume element. I mean, yeah, it's from how it looks, it already has the similarities with volume elements and Riemannian geometry, where we kind of take the wedge product of dual orthonormal basis. And the first fact is omega C is actually invariant under action of the special linear group. So if this means, so the special linear group acts on each entry. So I mean, first we can look at the tensor algebra. There it acts in every entry, and then it carries over to the Clifford algebra. And this is nothing else as to say that the volume element is does not depend on the choice of normal basis. And this tells us that omega C defines an element in the smooth sections to CLTM. Okay, and another thing that is easy to compute is that if we apply omega C twice, then we get the identity on the, I already specified here was to the spinor bundle from above. So, I mean, this works in every Dirac bundle. I mean, this is something that happens in the Clifford algebra, not specifically on the bundle. And the second fact is that the spinor connection applied to omega C, that's 0. I mean, it's also easy to see using, again, synchronous or orthonormal frames of TM, as we did in the first talk, I think. So where Nabla, where we achieved the connection applied to the to each basis element in the point where we consider it vanishes, and then again using the Leibniz rule for the spinor connection, and this two things together give us a orthogonal splitting of the spinor bundle into a positive part and a negative part, and these are the plus and minus 1 eigenbundles. Eigenbundles of omega C. And in the even dimensional case, this splits the spinor bundle in two parts, two parts with the same dimension. And with Clifford multiplication with an element of Tm, this is an isomorphism between these two subbundles, because as one can compute quite easily, every element in Tm anti-commutes with this volume element. And this does not work in the even-dimensional, in the odd-dimensional case. I mean, one can also define this volume element, but there it always acts as the identity, because elements in Tm just commute with the complex volume element. And this is, the splitting is also called the chirality decomposition of sigma m. And what's particularly nice about this splitting is that the Dirac operator actually splits, or actually is compatible with this decomposition, in the sense that it reduces to operators on sigma plus and sigma minus. We can already consider twisted bundles here, and it interchanges them. So this goes to sigma m minus plus tensor E, and that's because, I mean, we had this local form of the Dirac operator as sum over an orthonormal basis EI times sigma S EI, and sigma S, nabla S, and the applied to the volume element is just 0, so this commutes. And Clifford multiplication with an element of E commutes, anti-commutes with the volume element. So the Dirac operator anti-commutes with the volume element. And that's why it interchanges the two subbundles. And one usually writes this as the Dirac operator, the twisted one, has this block diagonal form where DE plus sits on the left lower corner and DE minus sits on the right upper corner. And now I also want to go to a smaller class of manifolds, namely want to also consider closed manifolds. And closed in this context means, or as always, probably compact without boundary. Because in this setting, the Dirac operator has quite nice properties, namely the E extends to a self-adjoint operator, joint operator on the closure. So with this, I mean the minimal closure and the functional analytic setup. And the domain then turns out as H1 sections to sigma m tensor E, going to L2 sections on sigma m tensor E. And it also turns out that this minimal closed extension is Fredholm. And Fredholm means that first the dimension of the kernel of the Dirac operator is finite, and also the dimension of the co-kernel. And it turns out that the difference of them is an invariant of the manifold, which we call the index of dE bar. And the issue now is with self-adjoint theorem operators. This is actually equal to the kernel of the adjoint of the operator, and since it was self-adjoint, this is actually the kernel of dE, so this is always 0. So this doesn't really help much, but we have the splitting, and it turns out that we can take instead the index of either the positive part or the negative part, doesn't matter, which is then the dimension of the kernel of dE plus minus the dimension, and it turns out the adjoint of dE plus is then dE minus, so here is the kernel of dE minus. And that is not always 0, and that's actually the part of the content of the Atiyah-Singer index formula. It's quite famous theorem, and it gives us a formula for the index of exactly this operator. Namely, we take the integral. So I will write down now some differential forms. I will not really explain them. You can understand them using Chern-Weil theory, for example. So these are topological quantities, and this second one is the Chern character of E, which lives in even degree differential forms on M, and the A hat degree, as it is called, lives in 0 mod 4 degree on M. So the first is a complex differential form, and the second, or the A hat degree, is actually a real differential form. And you can also understand this in a completely topological way, and usually then one writes this with the cut product, and we pair it with the fundamental form on M. So that's maybe first a bit surprising, because the right-hand side is a purely topological quantity. It does not depend on all the choices that we did. So on the left-hand side, the Dirac operator, we made a lot of choices. We choose a smooth structure, we choose a spin structure, we choose a metric, but it turns out that the index is does not depend on any of these. And I also should say that this integral here has to be understood. So these are differential forms which can have elements in different degrees, but we just pick out the top degree elements and pair it with the fundamental class, which is then the integral and the theorem setting. Yeah. So that's that. And I also promised to say something about scalar curvature. So there are different ways to define scalar curvature. So I choose here a very geometric one. Namely, if we take a Riemannian manifold of dimension n and pick some point in n, then we can compare volumes. Namely, we want to compare the volume of the epsilon ball with respect to the metric on M to the volume of an epsilon ball in the Euclidean space. So for the upper ball, we take the metric G as distance indicator, and in the lower volume, we take the Euclidean metric. And we can expand this in the point P, and we get 1 minus some prefactor 6n plus 2 times the scalar curvature of P epsilon squared, and then we have higher order terms. This is as epsilon goes to 0. And this tells us that scalar curvature kind of measures how volume grow in an infinitesimal way. So if scalar curvature is positive, it will tell us that volume grows slower than in Euclidean space, and if the scalar curvature is negative, volume will grow faster than in Euclidean space. And usually, so I never saw anyone using this particular definition for any computations, so it's useless for that, but it's very nice to see the geometric meaning of the scalar curvature. Usually you define it as twice the trace of the Riemannian curvature operator. And there are the usual model spaces for scalar curvature. So first Euclidean space, it's flat. Then we have the n-sphere, which has positive scalar curvature. And then we have the negative model space. I searching now for the name. Yeah, I think you mean what I mean. Hyperbolic space. No, sorry. Yeah. So these are the usual model spaces. And there's a famous theorem of Kasten and Warner. It's from 1975, which tells us that if we take any closed manifold of dimension at least 3, then we can take any and we take a smooth function such that there exists at least one point in M where f is negative, then there exists a Riemannian metric G, which is the scalar curvature of which is equal to f, where the scalar curvature is equal to f. So here you see already that negative scalar curvature is easy to get. So on every closed manifold, you will always find metrics with negative scalar curvature, but positive scalar curvature is actually obstructive. Not on every manifold you can find positive scalar curvature. So that's why people are more interested in positive scalar curvature than in negative scalar curvature. And there's one obstruction that is already known for some while now, which goes back to Llarull. Namely, if we take a closed spin manifold such that the A hat genus, which is the A hat class from before, from the Atiyah-Singer index theorem, integrated over M.
So I have one question here.
Yeah.
So the modulus spaces that you have written is with respect to the usual metric, like the Euclidean metric, round metric, and the usual hyperbolic metric, or that with respect to any metric?
No, with respect to the usual metric, so the Euclidean metric on our end, the round metric on Sn, and the hyperbolic metric on Hn. So of course, if we take any metric, then this can be anything.
Yeah, because this theorem then I can apply on Sn, and then I can get a different scalar curvature.
Yeah. So these, of course, with Euclidean metric, Euclidean round metric, hyperbolic metric. Yeah. So the theorem of Llarull tells us that if you take a closed spin manifold and the A hat genus of M is different from 0, then M is, and usually one writes it as PSC, so this stands for positive scalar curvature. So it does not admit a positive scalar curvature. And the proof is actually very simple. I mean, that's just an application of the Atiyah-Singer index theorem. We take any element in the kernel of D, and I should say from the Atiyah-Singer index theorem, we know that the index of D is just the A hat genus of M. This was the difference of the kernel of D plus minus difference of kernel of D minus. And so this tells us that we can either find an element in the kernel of D plus, or flipping the orientations, the index just gets a minus, and then we would find an element in the kernel of D plus, D minus. And this then also gives us an element in the kernel of D. And this we can put into the Schrödinger-Llarull formula, which then gives us on the one side. So I want to already integrate it with respect to the usual product that we'll get on manifolds. So I probably should say what this here is. So we take the integral over the manifold and take fiberwise then the scalar product of the spinor bundle. And then we also have that's that. And then from the Schrödinger, which formula we know that this is the Laplace operator applied to U. And 1/4 the scalar curvature applied to U and coupled with U. And one thing I didn't say yet, but I will just take it as a fact here. The connection Laplacian you can also write as the adjoint of the connection followed, or the spinor connection followed by its adjoint with respect to the scalar product on L2. So this is nothing else than as the spinor connection applied to U norm squared. Again, the scalar curvature. Okay, this is always positive. And if now the scalar curvature were positive, then we would immediately get a contradiction, because then this would be positive, which is a contradiction. So the A hat genus is probably the oldest obstruction that we have for positive scalar curvature. And now I want to come to the very famous theorem in scalar curvature geometry. There will be a theorem 2, so I call it theorem 1, which goes back to Llarull. This is basically the prototype of scalar curvature rigidity theorem. So we take a Riemannian manifold of dimension n, which is closed, connected, and spin. N should be at least 2. And we have further assumptions that the scalar curvature.
So if you can you go to the proof? Like I just have one clarity there. So the second equality, that d2u, the inner product of d2u with u is equals to the Laplacian of u with u plus this. So is it like it will directly come from this L2 inner product, or like is it some result that you are using?
You mean this here, this equality?
Yeah.
This is just Schrödinger-Lichner formula applied and applied to U. So I mean, you can write it as W plus 1/4 scalar curvature G U, and then paired with U.
I see. Okay.
Yeah. So the first assumption in the Llarull's theorem is that the scalar curvature should be bounded below by the scalar curvature of the round sphere in dimension n and with radius 1, because otherwise you with different radii you should would just get a prefactor. And then we have a comparison map going from M to the n sphere with the round metric, which should be smooth, and it should be topologically non-trivial, meaning that we want that the degree of f is non-zero. And in the two-dimensional case, f should be one Lipschitz, which means that distances are not getting bigger under applying f. And in the case n bigger or equal than 3, f should be what's called area non-increasing. Which says that so from the differential of f, we get an induced map on two forms on Tm to two forms on Tsn. And this map should have norm at most one at every point. The one Lipschitz you could also characterize by Tf should be at most one at every point. And the conclusion from this is that f is then already a Riemannian isometry. And these are, I would say, quite not really strong assumptions that we take here, and we get a really strong conclusion out of it. And one special case I want to remark here is if we take the SM, the n sphere, as f the identity. So we start from any metric on Sn with satisfies the assumptions above to the Sn with the round metric. Then this tells us that G is already G0. So in this sense, the round metric on the n sphere is rigid, or we call it rigid. And I want to show you the proof of it. It's not too difficult, and it's actually really the prototype of all the following scalar curvature rigidity proofs, because they're all just modification of it, where the basic idea is the same, just the analytic details are more complicated. So, as explained above, we will take the spin bundle on M, the canonical one, and also on the n sphere. So these are the spinor bundles together with the spinor connection. And we define, I should say, maybe include the connection here in the notation. So I will call the spinor connection on Sn by nabla 0, and here let's say just nabla. And I want to define a twist bundle on M by taking the pullback of the spinor bundle on Sn. And this gives us the the Dirac operator that we are interested in. So namely this twisted Dirac operator. And now there are kind of two parts of the proof. Namely, the first one is we want to apply Atiyah-Singer. To find some element in the kernel of the Dirac operator. And here, as I said, we only have this Atiyah-Singer index theorem in even dimensions. So first, let's stick to n even. Then, as explained above, we get this duality decomposition of the spinor bundle. And also that this operator here is Fredholm. It's not a conclusion out of it. So this is Fredholm. And we can compute the index of dE plus or dE minus as you like. So that's the A hat class of M coupled with the Chern character of E coupled with the fundamental class. So yeah, this is a computation with characteristic classes. I mean, I didn't actually tell you what these characteristic classes are exactly, so I will just skip the computation. It's not particularly hard, but you will get the degree of f times the Euler class of the n-sphere. And that was supposed to be unequal to 0. And this, we can actually compute this just 2 in for n even. So that's in particular non-zero. And from this, we get what's called an harmonic spinor. Which is just an element in the kernel of the Dirac operator. And for n odd, I just give you a hint what's happening here. So in the original proof, Llarull considered the Dirac operator. So we did a dimension shift by considering m times s1 with a word product metric g plus r squared g s1. And then doing some limiting construction where the radius gets sent to infinity. This again yields a harmonic spinor actually of dE on M. Yeah, some people consider this as a dirty trick. There's a newer method using spectral flow I will not go into detail yet here, but this is kind of a odd dimensional analog to the Singer index theorem in even dimensions. So good. We have this element in the kernel of the Dirac operator, and that we can put into the Schrödinger-Llarull formula. And also one fact that I will not explain here, you can do some regularity theory for elliptic differential operators, and it turns out that eigenvectors of elliptic differential operators are actually smooth. So this is actually a smooth section to this bundle here. And yeah, let's put this in the Schrödinger-Llarull formula. So again, here we have dE squared applied to U and coupled with U in this L2 scalar product, and or dE bar, let's say, and dE, as I said, is self-adjoint, so that's the same as dEu norm squared, which is by assumption 0. And now the Schrödinger-Llarull formula tells us that this is the connection Laplacian, and as I just said before, this we can write as the adjoint of the spinor connection, and applied to the spinor connection, then applied to U. Then we have the scalar curvature term. And in addition, we have this curvature operator here. And this is, as before, the norm of nabla U squared. Okay. Here we can already insert what we assumed in the theorem, namely that this is at least 1/4 the scalar curvature of the round sphere and norm U squared. So what's left, or we can also say that this is positive, and what's left is to analyze this last part here. Namely, we can, so the following computation is a local computation, so we can do this at every point x in M. So we take the curvature operator applied to U with this fiberwise scalar product. Then the definition of the curvature operator was that we take the sum of I smaller j and then of normal basis or of normal frame on M, the IIJ applied to the curvature operator of the Swiss bundle, and we insert EI and EJ, U. So this was just the definition of the curvature operator. And it turns out that, I mean, E was the pullback of the spinor bundle. So this is actually or one can show that it's the same as the pullback of the curvature operator the spinor bundle. So maybe make brackets here. And okay, there's some fact I also just want to use here and not really explain. So on the sphere, the curvature operator of the spinor bundle has a particular easy form, namely it's just Clifford multiplication with the push forward of, or it's the curvature operator is just the elements that you take in, just the Clifford multiplication of it. So already with this push forward applied, we would get push forward of EI, Clifford multiplication of push forward EJ, and then Clifford multiplication with U. And here this tensor product is because we had this twisted bundle of sigma m tensor E. So and these first two vectors are act on the on sigma m, and the second two vectors act on the second vector, namely the spinor bundle of the sphere. And now comes a fact from linear algebra, namely the singular value decomposition. Which tells us that we find some orthonormal basis of Tfx Sn and real numbers u1 to un in Rn, such that the push forward of EI at the point x is the same as mu I EI. And since f was assumed to be a one Lipschitz, these mu i's actually lie between 0 and 1. And we just insert this here now. So continuing here, we get sum I smaller j, mu I, mu j, ei, ej, and so epsilon I, epsilon j, u, u. And now, first, so Clifford multiplication with norm 1 vectors is an isometry. So we can actually bound this below by taking just the norm of u squared. And this here is by the assumption that here actually I said something wrong. So f is only one Lipschitz if n is 1. So this is only if n is 2. And for n bigger or equal than 3, that this doesn't have to be the case. But what we know is that all products of 2 mu I mu j is bounded by 1. This is the area non-increasing assumption. And now, okay, again, bound this below, making this mu I mu j's bounded by 1. And then we use the formula of Gauss, which says that the sum of I smaller j is nothing else than n times n minus 1. So that's should look very familiar, because that's actually the negative of this term here. So what this all computation here tells us is that this whole expression here is bigger or equal than 0. And we started already with 0 on the left, and have here 0 now. So we have to have equalities everywhere. So also here and here. So the conclusion out of this is that the scalar curvature of G has to be equal to n times n minus 1. And first, these products have to be 1 for all I are equal to j, and dimension at least 3 with some combinatorics, because here we have more than one equation. We get that mu I is 1 for all I. This fails in dimension 2 because we have not enough equations here. And so in dimension 2, we have to assume that F is 1 Lipschitz. And this tells us that F has to be a local isometry. So the differential of F at every point is an isometry of the tangent spaces. And from Riemannian geometry, we know then that this map here is a Riemannian covering. And since Sn is simply connected, this has to be an isometry. So that we get our conclusion. So I hope it wasn't too fast. Are there any questions to the proof of Llarull's theorem? I mean, I left out, of course, some details.
Hello.
Yeah.
So in the n equal to 2 case, how do you conclude that? Can you repeat once?
Sorry, say again.
Yeah, for the n equal to 2 case, how you are concluding that F is Riemannian isometry?
I mean, in the n equal 2 case, we are in this case.
Yeah,
and I mean, if the product has to be 1, yeah, at this point, if the product has to be 1, and you can exclude -1.
right.
Yeah. Actually, that's a mistake in the original paper of Llarull. So he actually didn't see this. So he just wrote area non-increasing for all dimensions. But that's just a side remark.
Okay.
Yeah.
So, is there any non-trivial example other than the identity map on Sn? Or you can use this theorem to get something interesting. Like identity kind of seems bit okay. It should be kind of though it's not in general, but like for any other manifold, like for like, there's there are like at least two conditions. So conditions seem to be like why I should have those condition kind of thing. That's why I'm asking.
Um, so you're asking if there are some applications of
Yeah,
to the
yeah, yeah.
Mm, yeah, actually, I don't know for sure. So, I mean, yeah, geometers are interested in this. I mean, because of you get out such strong results from very weak assumptions, but as far as I know, there are not really obvious applications of this. So actually, when Llarull published this, no one was really interested in the stuff, and it only got interested to people when Gromov digged this out again, and then everyone wanted to do scalar curvature rigidity. So that's a prime example how mathematics works.
Right. Like the first condition, the scalar one, the lower bound is 6. The second condition, I don't like. It seems bit why suddenly this condition should be there, kind of thing. Like ape kind of. If I just from see from the like homotopy perspective, ape is kind of a element of co-homotopy groups kind of thing. There but like in the three or higher case, you want your it to be area non-increasing.
Yeah. So I mean, if you assume one Lipschitz, that's implying area non-increasing. So one Lipschitz is actually stronger.
Uh,
Um, yeah.
hmm. Right.
Yeah. I don't know if this is already an answer.
Yes, thank you, thank you.
So on his question only, like if I'll assume F to be, see, of course, and if I'll assume antipodal map, then it satisfies this condition, I believe.
Yeah.
But there, I guess we will not get anything extra. But if I'll assume F to be a like okay, it's already, yeah. If I'll assume a rotational map, that's already an isometry. So
Yeah.
can you, like, I don't understand this area non-increasing in geometric way. Can you like
Yeah. I mean, would be something like you have your manifold M here and your sphere here, and then look at some point and some area in the tangent space to this. Uh, how can I keep this here? So if you look at this area, this gets to send to some point here, f of x, and then you again look at the tangential space, and this area then has to be smaller than the original one. That's a way how to geometrically interpret this area non-increasing.
oh, I see. Okay, okay. And one
to
like it's a layman question, but like so on Rn, so
yeah
like the scalar curvature is always zero, no, for any metric,
on
or
Rn.
yeah,
No, you can
okay,
just yeah then you can just deform it locally to have some bump or something. And of course, I mean, in 2 dimensions, this does not say much, but in 3 dimensions, you can think
okay,
of
I
some
see now. Okay, okay,
functions, and you can, yeah, get also other stuff for the scalar curvature.
right. Okay,
And
okay,
actually,
okay.
the hyperbolic space itself is just an Rn with a different metric.
Okay, I see.
Yeah, so in these theorem, I also have like a query about the closed. So you on the closed manifold, if you have a function, smooth function having at a point non like negative value,
Uh,
then you can construct a
you mean custom Warner, yeah?
yeah, this one. Yeah, so is there any like compactness is necessary here? Like is there anything uh
I mean,
like
if you assume non-compact, then
yeah.
you can realize any scalar curvature again, because yeah, then you can kind of move this into this open end, or if you have manifold with boundary without any assumption on the boundary on the curvature near the boundary, then you again can realize any scalar curvature. So for the case of compact manifolds with boundary, we have to assume something on the mean curvature on the boundary to get some meaningful or some yeah interesting theory about positive scalar curvature.
And is there any kind of naive reason why you choose n to be greater equal to 3, not like in the 2 dimension? Is there any exception kind of thing?
Mm, actually, okay. Mm, I mentioned two. I'm not sure what's actually happened there. I
Oh, okay.
mean, they are close, so the amount of closed two manifolds is quite small, I would say.
True.
Um, so I would suppose that it's a bit more restrictive there. And in dimension 2, actually, now that I think of dimension 2, the scalar curvature is nothing else than the Gauss curvature, or yeah, so or the um, scalar curvature, yeah, is the same as, or gives you the same information than the whole Riemann curvature tensor. So the notion of scalar curvature is there is not weaker than um, sectional curvature. So that's probably a big, or that's the a very big difference from the case n bigger or equal than 3.
Oh, okay. Right. Like in the just in the sphere case, I'm thinking like whether like is there any function which takes and like it's less than 0, but there does not exist any Riemannian metric kind of thing on the sphere itself.
What? Say again?
Like if I just take the my closed manifold M to be sphere, 2-dimensional sphere.
Yeah.
and like consider a smooth function on that, taking a negative value at some point. Thus, that says that there does not exist any metric on H2.
So on S2, I think
Yeah,
probably you can. I'm not sure. So I would think that you can also get any scalar curvature, but don't quote me on that.
right.
There's actually a famous theorem which tells you for the torus, for any
Right.
torus, that if you take scalar curvature on the torus bigger or equal than 0, then it's actually already a scalar flat. So on the torus is one example where you cannot find a positive scalar curvature.
Uh,
And also in dimension 2, I think it's also true.
oh, okay. Thank you.
Yeah, you're welcome. So actually I wanted to talk about one generalization of this. Maybe let's just make this quite fast. So this goes back to Simone Cecchini, Bernhard Hanke, which is my supervisor, and Thomas Schick from 22. It says that if we take a smooth, closed, connected spin manifold of dimension n at least 2 even, and now okay, people ask, especially Gromov, which assumptions in the Llarull theorem do we really need? And actually, it turns out that we can weaken the assumptions quite a lot. Namely, the first thing that we can assume is that G does not have to be smooth. It can be regular in a Sobolev meaning, namely it should be in W1P the image in this symmetric two tensors, and P is at least n. I mean, that's the reason is here the Sobolev embedding theorem, and also some stuff that we needs P bigger n, and these are called in their paper admissible Riemannian metrics. Such that get a scalar curvature. Before it was a smooth function. Now we cannot define scalar curvature as a function because we have to differentiate twice. But what we can still do is we can define it as a distribution. So integrate against some test function and then pulling over the second derivatives to the test function. So we can still make sense of this inequality in a distributional sense. And this goes back to Lie-le-Floch. And for the second, so we again have such a comparison map. And now, so before F was assumed to be smooth, but one can relax this to be have to be Lipschitz. So can have any Lipschitz constant. I don't assume at this point to be Lipschitz constant equal to 1. And again, the degree should be unequal to 0. And for n equal to 2, it should again be Lipschitz. And for n bigger 3, f should be area non-increasing. And here I should say, so Lipschitz functions, there's a theorem of Rademacher, which implies that every Lipschitz map is actually differentiable almost everywhere. So we can also make sense of this area non-increasing assumption, but only almost everywhere. And the conclusion here is that so here with dg, I mean the induced Riemannian distance induced from the metric to the induced Riemann distance from the round metric. This is a metric isometry. And metric isometry I know really means something weaker than Riemannian geometry, isometry. So we can not conclude in all cases that it's actually a smooth map. Okay, that's this generalization, and actually I want to talk about it because in a new version where I was involved too, so we uploaded it to archive this year, we also considered the odd-dimensional case. And yeah, it's already quite late, but I just want to indicate here in the proof what you have to, what's different now. As I said, so the whole idea of the proof stays the same, but the analytical problems are a bit harder. So first, the spinner bundle. So we constructed it out of a smooth metric, and it's not clear actually how to construct spinner bundles out of metrics that are not smooth. But there's a workaround, namely we construct this spinner bundle with respect to a smooth background metric. And so this map F here was not only Lipschitz, not smooth. So this pullback bundle here will only be a Lipschitz bundle. So here for this twist bundle, we cannot work with smooth sections. We have to work with Lipschitz sections, and this will have image in EL2 sections. And yeah, there's a way to kind of translate the Dirac operator from one spinner bundle to another spinner bundle. So we have this hypothetical spinner bundle with respect to this non-smooth metric, and we kind of translate it to this spinner bundle of this smooth metric, and it still has these nice properties. Namely, its extension is self-adjoint and pattern and so on. And then we can think about what the Artinger-Singer index theorem in this case might tell us. And here, at this point, one can consider an approximation of this non-smooth metric. So we approximate G by smooth metrics, and we get a continuous family of Dirac operators. So what I want to say, we take a path from a smooth metric to the metric G, where all metrics but the G are smooth metrics. So we can actually define the Dirac operators and also can define the index of it. And then we use that the index is invariant under continuous families of Dirac operators. So we still can compute the index. It is the same, so it's non-zero, and we get a harmonic spinor out of it. In the odd-dimensional case, I will postpone this to next week because there it's a bit more difficult. So this trick here with S1 doesn't work in this setting and has to work a bit harder. Then looking at the Schrödinger-Lichner-Ridge formula. So this regularity theory now doesn't work anymore. So we really have to work in H1. So especially we cannot write here this expression because the coefficients of the Dirac operator will not be differentiable anymore. So this does not exist, and also this here. So, but this and this very well exists, and using a limiting process, again starting from smooth metric and so on, you can actually get a Schrödinger-Lichner-Ridge formula in an integrated form, and still can make these conclusions here. So we have on the right hand side, left hand side, you have this. On the right hand side, you have this, and here, I mean, we have this now in a distributional sense. And yeah, this term here, you can also make sense out of it. And then this local computation here, just do it almost everywhere, because these differentials are not defined everywhere, but almost everywhere is enough for us because we just consider it under the integral. And we again get this conclusion here. Again, get that here we all everywhere have to be equalities. And we also get this conclusion, these conclusions here, with the difference that you only get local isometries almost everywhere. But now this does not work anymore. So we don't get, or at least not in every case, we don't get that is a covering mech. So yeah, then one has to work a bit because local isometry is not already metric isometry as I wrote here, but there is some trick that was invented by Cecchini, Hanke, and Schick, how to extract some informations on the on the harmonic spinner that we constructed using the Athena single index formula, and then use some some theory from quasi-regular maps going back to Reshetniak. Then one has to do some hard analytic computations, and one actually get that F is a metric isometry. So what one has to show to get this is that the F is orientation preserving almost everywhere, and from this Reshetniak, yes, we get that F is a metric isometry. Okay, that was maybe a bit fast. Sorry for that. But I wanted to tell you that the general idea is still the same, but all the analytic details are more difficult, and you have to work to really get there. So here's the theorem again. So maybe let's stop here. Thanks for staying.
Okay, so are there any further questions?
I just have a
Okay, then let's. Sorry, yeah.
In the original proof of Llarull's theorem, there the theorem is true only in the even case.
What?
Like in the assumption, there you took the n to be only even.
You're talking now about
In the original Llarull's theorem.
So it's true in all dimensions. Only in
Any
all dimensions you have to do some twist.
okay. So I just in the proof I don't see like where you use the
Yeah, I was quite short about this. So in the odd dimensional case, you have to do some tricks or use spectral flow. I didn't talk about that.
Okay.
And you still get this harmonic spinner, but Atiyah is only gives you something in even dimensions.
Right. So the similar trick will also work in your case also, have to some modification of that works in your case also.
In our case, I mean, it's a bit subtle. So this does not work here.
Okay.
Or I should say, with this assumption here, that P is bigger N, this does not work. If you assume that N is, or P is bigger N minus 1, then you still get out of it a harmonic spinner, but and you get local isometries. But this trick that Cecchini, Hanke, and Schick used to conclude that symmetric isometry does not work, unfortunately. So from this point, you don't get a metric isometry.
I see.
So actually, local isometry, so we did, I will go into this a bit in more detail next week.
Sure.
But one has to work a little bit more.
Okay.
Then we can thanks Lucas, and we will meet again on next Wednesday at the same time. Yeah, probably
Yeah.
for you, Lucas, it will be 1 hour earlier than
Yeah,
this
probably.
week. Yeah. Okay then. Bye.
Yeah. Yeah.
See
See
you
you.
next
Bye.
week.
Thank you.